Hi, welcome to another fundamentals video. We're going to carry on from our previous series on DC fundamentals by introducing DC circuit transients, or more in particular LC circuit transients, i.e. inductors and capacitors, because with our previous videos we've looked at, they've just dealt with voltage sources, current sources and resistors. And when you deal with those sorts of circuits, when you make a change to the voltage or the current, they change instantaneously. And these resistive circuits we've looked at, they're called steady state circuits because, well, when you change something, it just instantly changes and then it's steady. That's not what happens when you introduce capacitors and inductors into your circuit. They actually take time to charge up and discharge and do other stuff. So we're not in the realm of steady state anymore. We're in the realm of what's called transient circuits. So we have to start this off by quickly recapping what is a capacitor, what is an inductor, and then we'll get into series and parallel capacitors, series parallel inductors, and then how they charge and discharge and do other stuff. Let's go. Interestingly, it's always referred to as LC. It's never CL. Don't know why that is. It's just a thing. Now, the thing with capacitors and inductors is they can actually store energy. Capacitors actually store energy in the form of an electric field across a dielectric material, and inductors store energy in a magnetic field. And we can actually use these properties to useful effect, as we'll see in future videos. But it's the fact of when you build up the energy in these devices, then that's why it takes time to build that energy up and then to discharge that energy from them. Whereas something like a resistor, it will be dissipating power when you apply a voltage to it, but it will never store energy. As I said before, as soon as you remove the voltage, for example, there's no more power in a resistor. It just instantly vanishes. Whereas these suckers, they can store things, and that makes things a bit complicated. Now, a capacitor is just two metal plates separated by a dielectric material, so there's no direct electrical connection. It's essentially an insulator, and that dielectric material can just be air. You can just have two plates or two wires side by side like that, and that's a capacitor. There's capacitance between me and that camera I'm looking at now. It's just, you can actually calculate it. In fact, a common tricky exam question might be, what's the capacitance between the Earth and the Moon? Figure it out. Anyway, that dielectric material, it can be air or it can be any of the poly, put the kettle on materials for those poly whatever capacitors that you got. It can be one of the various types of ceramic material for your ceramic capacitors or whatever. And basically air has a dielectric constant of 1. Most other materials are going to have a dielectric constant greater than that, and that just basically, as you increase the dielectric constant, it just increases the amount of capacitance that a capacitor actually has. But anyway, when you've got two plates and you apply a voltage in here, then you'll actually get charge build-up, positive and negative charges on both of the plates like that. So a capacitor will charge up until the voltage across the capacitor reaches the voltage source, and then that becomes a steady state. But once you then remove the voltage from the capacitor, that voltage stays on that capacitor. It's stored in there. There's energy or charge stored up in that capacitor. And one of the basic equations that we've actually got is charge is Q equals C times V, or the capacitance times the voltage. That's one of the basic electronics formulas you've got to remember. And charge is in coulombs. And 1 coulomb is actually 6.24 times 10 to the 18 electrons. So it's a build-up of electrons. And your capacitance is measured in farads, and a farad is actually a lot of capacitance, and V, of course, measured in volts. But that's your basic formula for charge. You don't often have to use this, but it's important to know. It's one of the fundamental equations. And of course, you can deep dive down into the physics side of all this and things like that, and we won't do that. We're sticking to the practical electronics side of things. Speaking of practicality, capacitors in series and parallel. I've drawn 3 here, but you can have as many as you want, or you can have 2. And the formula you might actually recognize from our resistor videos. The total capacitance CT of these 3 capacitors in series is 1 over all of 1 over C1 plus 1 over C2 plus 1 over C3. And that formula should be familiar to you because it's exactly the same as the parallel resistance formula, except it's kind of flipped now because our capacitors are in series, whereas that exact equation, just replace C with R, and it's exactly the same for parallel resistors. And yes, just like parallel resistors, if you've only got two of them, then you can use that alternative formula, C1 times C2 over C1 plus C2 gives you your total capacitance. But if you've got more than two, then that formula applies. And for parallel capacitors here, the total capacitance is just C1 plus C2 plus however many capacitors you got in parallel. And of course, that's the same as your series resistors. So just think of resistors and capacitors as opposite. The same formula applies, just in the opposite case. Easy. Now let's go back to capacitors in series here for a second, because it's important to remember that the total charge Q is the same on each capacitor. It's a bit counterintuitive. The charge on C1 will be the same as the charge on C2, which will be the same on charge on C3, and that equals the total charge of the circuit. Now, with ideal capacitors, when you actually have them in series like this, you will actually get an equal voltage on each capacitor like this. V1 will be equal to V2, which will be equal to V3. Assuming they're ideal capacitors, they're all balanced and everything else. Sometimes you'll actually find what's called balance resistors actually in parallel with series capacitors like this. You'll find these commonly in like power supply, high voltage power supplies and things like that, just so there's just to help balance out the capacitors due to just, you know, practical differences in the capacitors. So anyway, that's just a useful thing to know. And it also helps discharge them as well. Handy. So I'm going to take a little bit of a tangent here and actually use the fact that the total charge is equal also to the same charge on each of these capacitors, and that we can actually derive the formula based on this for that, using that particular fact. So I've squeezed it all in down here, so please forgive me, I've run out of room, but charge Q equals capacitance times voltage up there. So as I said, the total circuit charge is equal to the charge on C1, which is equal to the charge on C2, which is equal to the charge on C3. You don't add them up. So the charge is equal to C1 times V1 is equal to C2 times V2 is equal to C3 times V3. And if we rearrange this formula, voltage equals charge on capacitance. Therefore, voltage 1 here equals the charge Q1 on C1, and voltage 2 equals charge on Q on C, and the same for the voltage across 3 as well. Now, if we take this formula, the total voltage equals the voltage across C1 here plus the voltage across C2 plus the voltage across C3. The voltages add up, and if you just substitute that in, I should have a arrow pointing over to that, then V is equal to Q on C, which is in V1 is equal to Q on C1, Q on C2, Q on C3, which then translates into our formula over here. 1 on C, well, that should be CT total. 1 on CT equals 1 on C1 plus 1 on C2 plus 1 on C3. So you just move those over and you get that formula, 1 on C1 plus C2 plus C3. And that's how you can actually derive that from that. It's just an interesting little aside. So you can think of the charge as the current in a series circuit. I know this is not a good way, but it's basically the current will be the same for all of them because it's series. Likewise, the charge will be the same for all of them. So we'll work on transients after we've covered inductors. So let's have a look at an inductor. When you pass a current through any wire whatsoever, any component, any PCB trace, doesn't matter what it is, when you pass current through, there will be a magnetic field. So that's why I've got a wire here, just a straight wire like this. You've got current I passing through it. It will generate a magnetic field around it. And you might ask, which direction is the magnetic field flowing? Well, there's a handy little rule which you should remember, which is called the right-hand rule, and it involves exactly this. It involves a single Fons thumbs up. It's the right-hand rule. Take your right hand like this, point your thumb in the direction of the conventional current flow, none of that electron current flow rubbish, conventional current flow like that, and your fingers like this will point in the direction of the magnetic field. That's called the right-hand rule. So there is a magnetic field around every inductor. That's why you can add like a little ferrite bead. You've probably seen these on circuits, a little wire with a little ferrite bead around it, and that is essentially an inductor. The ferrite bead just helps sort of contain the magnetic field in there, makes it a bit more effective. But anyway, the way you usually make inductors more effective is to have multiple turns, i.e. make them into a coil, and they can be a physical air coil like that, open any RF radio tuner, something like that, you know, old school ones, and you'll find then they actually have like little just coils of wire like that. And when you coil them like that, the magnetic fields actually add up and pass through the multiple coils. So that's why you wind inductors into a coil, because and then you can put like ferrite cores through them, or you can make them into transformers, and you can do all sorts of stuff. That's going to have to be the subject of a future video. But yeah, inductors are more efficient when you wrap multiple turns around them. So the magnetic fields just add up in the coils, and it's more betterer than just a straight wire like that. So just like a capacitor, we can actually store energy inside the magnetic field like this. So when we apply voltage to it, we'll look at how they charge up and discharge in a minute, but we can actually store energy in a magnetic field so that when you actually release it, there's a few traps for young players when you release a voltage or the load from the inductor. If voltage can skyrocket, we'll take a look at that in a minute. Anyway, I'm getting ahead of myself. We've got another basic formula, bread and butter stuff you've got to learn. You won't use it all that often, but you've got to understand the concept. Is basically the voltage at any instant in time, that's why it's the instantaneous voltage, in volts of course, is equal to the inductance, which is measured in henries. Once again, a henry is a very big, just like a farad is a very, very big value of capacitance, a henry, very big value of inductance. And that's multiplied by di dt. And don't freak out. It's basically, that just means the change in the current, I, over the change in time, like that. So some people might write it as, you know, delta I or delta T or something like that. But di dt is just how your mathematicians, you know, put it. And these are lowercase v, I, and t to designate that there's sort of like instantaneous values. So at any instantaneous point in time on the graph, as you will see shortly, that's what your voltage is going to be equal to. So if you've got a 1 Henry inductor here and you've got your current change in 1 amp per second, di dt, change of current in over time, 1 amp per second, that'll give you 1 volt. Got it? It's a basic formula. And I don't like to do this, but I'll briefly mention it just for a bit of completeness. Then we're talking about Faraday's law of electromagnetic induction, and you can go look that up, but we get more into the physics side of things, and that is E in volts is equal to minus N, which is the number of turns, and d phi dt there, as it's called, that's the rate of change of magnetic flux in Webers per second. Now, the negative here, this is actually Lenz's law, and you can go look up that up, but it basically says that the voltage is going to be the opposite of what change actually produced it. So that's where the negative comes from. Anyway, that'll actually be important in the discharge side of inductors when we look at that next. So anyway, inductors in series and parallel, it's opposite to capacitors, and it's the same as resistors. When you have inductors in series like this, it's just the total inductance L is just L1 plus L2 plus L3 in henries. And when you put them in parallel, the total is, once again, this same equation. It's exactly the same, except you replace C with L, like this, in parallel. So if you simply remember your resistance, parallel, and series formulas, you'll know that capacitors are opposite because they're not resistors. They're an open circuit, whereas inductors are basically the same as resistors because measure an inductor at DC and it's practically 0 ohms because it's just a piece of wire. It's a resistor. So the formulas actually work out the same, except your inductors can actually store a magnetic field and your pure resistances can't. Although in practice, when you're talking about practical electronics components, every resistance has a little bit of inductance. Every capacitor has a little bit of inductance in the leads. And then every inductance has some capacitance across the coils. And it's just the practicalities of real components is, yeah, they're never ideal, but for most purposes, near enough. And once again, just like we derived the formula down here like this, you can actually do the same thing from your basic formula to derive this from this. Try that at home. So now we move on to the transient part of this. We'll first look at RC transients, and then we'll look at LC transients, i.e. resistor, capacitor, transients. And as I told you before, there's a charge curve and there's a discharge curve, because these aren't resistors. These actually store energy. You build up charge or energy into them, and then you can extract energy out of them. So this is our charge curve, this is our discharge curve. We've got a basic RC circuit here. We've got a voltage source V. We've got a switch that we can just switch to in the up position here. It charges up the capacitor through this series resistor R here. So once it's charged up, then we can switch this over to short it out to ground, and we can discharge the capacitor through that same resistor. So let's take a look at what happens here. So what we've got is capacitance C, resistance R in farads and ohms, of course, and then we've got a voltage across the capacitor, which is designated VCT. That just means that it's changing over time, because remember, we're talking about differential calculus here, basically. Ooh, scary, but we're talking about a change in voltage over time here, something changing. That's what differential calculus is. It's just like looking at things changing over time. So in this case, we've got our voltage here versus time, and the voltage is going to rise up like this. And you might notice this curve, it's an exponential curve, and hence why in the formula down here we've got E, which is an exponential function. So let's assume that our switch is down here, our capacitor is completely discharged, there's no voltage on it whatsoever, and then we suddenly switch it over up to here, and we've got our voltage of, say, 1 volt here. Then it's going to charge up until it eventually gets to V here, or 1 volt. It's going to slowly charge up like this, and that time constant is going to be dependent on the value of the resistor and the capacitor here. Now I should have actually wrote this rule on the board, but I kind of ran out of room. So here's the #1 rule with capacitors. When they're discharged, when you suddenly apply a voltage to them, they act as a short circuit, because remember our formula up here, Q equals C times V. If there's no charge on the plates of those capacitors, if it's completely discharged, then the capacitance, it doesn't matter, 1 microfarad, it can be a farad, it can be 1,000,000 farads, doesn't matter what it is. If you've got no charge, then you're going to have no volts, because volts equals Q divided by C. 0 on C is 0. So that's why as soon as you apply the voltage over here to a discharged capacitor, this capacitor, it's a short circuit. And this is why you can actually get lots of issues with large values of capacitances, particularly in power supplies. Have you ever wondered why, when you often plug a mains cable into a big thumping power supply that has big DC capacitors there after the rectifier, and you might get a spark or something like that? That's because there's a lot of current flowing, because the capacitors are a short circuit. So you're going to get this surge of current flowing, and the current, of course, will be, because this capacitor is a short circuit, will be just V divided by R. And that series resistance in, say, a mains 240 volt power supply, there's really not much resistance there. You've got the connectors, the wires, and then you've got basically the diode, the equivalent DC resistance of the diode bridge rectifier, and that's pretty much it before it gets to big thumping capacitors. So the inrush current is going to be very large. This is why a lot of power supplies will actually have a slow blow fuse, because if you put a fast blow fuse in there, the inrush current caused by the capacitors being a short circuit can blow fast blow or quick blow fuses. So that's why you put a little fuse in there that's got a little inductor, which we'll get into. It acts kind of like that, and it's a slow blow fuse that will then prevent that large inrush current from actually blowing the fuse. Slow blow fuses. important practical aspect of this. Right, so your capacitor is a short circuit. It starts out at 0 volts here, and over time it starts to charge up like this. Now, the initial rate of charge will be the quickest, and then it will slowly taper off as an exponential function. And this is our rise formula, that one of these fundamental formulas you should remember. And this formula applies to both capacitors and inductors, as we'll see in a minute. But so VCT, which is what I said, is just the change of voltage over time. It's the instantaneous voltage. So the voltage at any instant in time t here, I've written VC because it's the voltage across the capacitor, is equal to the maximum voltage, so you can think of that as V max, or your source voltage, multiplied by 1 minus e, which is an exponential function. That exponential function is that weird little e to the power of x on your confuser here, to the power of minus t, so minus whatever the time period is you're talking about, divided by capital T. Not the same thing. Capital T is not the time here, that's little t like this. Capital T is actually R times C, and this is called the RC time constant. And you'll see this all the time, and it'll give you like a rough ballpark of how long it takes to charge up a capacitor. And you'll see the RC time constant in lots of things, like the 555 timer, for example. The formula for a 555 timer is 1.1 times RC, the time constant. We might look at why in a minute. So anyway, it rises up fairly quickly, and then it follows the exponential curve, and eventually, after about, basically after an order of magnitude, after about 10 time constants, you can pretty much say it's equal to V. In theory, it never gets there, but that's for those math nerds. In the real world, it does. And coincidentally, this is the discharge curve that we're going to look at, the fall curve, but it's also the current, because, as I said, the current will be a maximum. Just imagine that's not V, imagine that's I, current I. Current will start out as a maximum, which is V on R. You can't get any more than that because of the pesky series resistance. Then it starts out at maximum, and it follows basically the inverse of this curve like this until we eventually get no current whatsoever. And that will be designated IT here, like that, because it's the value of the instantaneous current at any point in time. Now, here's an important thing to realize. This RC time constant, it's actually an important number. It's actually 63.2% of the charge. Let me show you why. Basically, if you follow the initial charge curve like this up to there, okay, if at its initial point, if you went in a linear fashion like that, and then you dropped this down here like this point here, it'll be equal to 63.2% of the maximum charge. And if you take that down there, that is 1T. And then you'll have 2T here, and 3T, and 4T, and so on at that time period. That is called the RC time constant, but that's how it's actually derived. It's 63.2%. And like that number means something. If you ever see 63.2%, you know you're talking about RC or LC time constants. So assume our capacitor is fully charged up to 100%. If we now flip the switch over to here, we start discharging the capacitor like this. So it starts out, this is our discharge curve, this is our fall curve here. And once again, it's VCT, which is the instantaneous voltage at any point in time. It starts out at V, which is what we charged it up to, starts out at, if this is 1 volt, it starts out at 1 volt, and then it discharges like this. And once again, time constant is exactly the same thing. If you follow that curve, it's a bit dodgy, but if you follow that curve, trust me, and you'll get to a value of 36.8%. Once again, if you see that figure, either of those figures there, you know you're talking about LC or RC time constants. And there's another formula you have to remember for the exponential decay or exponential fall in voltage. Once again, VCT equals V times exponential to the power of negative t on t. It's exactly the same equation, except there's no 1 minus. And you can see why there's a 1 minus in there for this, because V, you've got to, you subtract 1, whoop, you start out at 0. It just means you start out at 0, whereas this one, we don't start out at 0, we start out at V, so we don't have the 1 there. But it's exactly the same equation. Once again, it's negative t, which is the actual time constant in here, over capital T, which is our RC time constant. Just multiply the resistance in ohms by the capacitance in farads. Now we have to get onto inductors. So I've changed it to LC transients here, and I've made a couple of changes that looks near identical. Of course, I've changed it to an inductor. That's our inductor L there in henries, and I've got the voltage across the inductor, VLT, and I've got the current through the inductor, which is IT here. Same resistor, same switch, same voltage source, same everything, and similar, well, identical curves. They're exponential curves, and once again, the exponential rise here, instead of voltage, we've now got current equals I've put I0, you could say I max. The 0 means like time 0, so I or I maximum, which will be V on R, of course. That'll be the absolute maximum current you can get out of this thing, and that's multiplied. It's exactly the same formula, minus T over capital T, which is the time constant. The time constant has now changed. Instead of R times C, it's now L on R. So you can substitute L on R in there, and some people write this equation as R minus RT on L, and it's exactly the same thing, because if you put that and flip it over. Anyway, if you rearrange the formula, it's exactly the same thing. And then the exponential decay, it's called, I've called it 4. It should be decay is the better, the more traditional, more correct term for it. Anyway, IT, it's exactly the same. We've now got, instead of voltage, we've got current at time 0 and times the exponential minus T on the time constant. And that's it. So we've got to have a look at the graphs now. Now this one is different. This is now, it's exactly the same graph as before, but it's now the voltage across the inductor here, down here, and this is the current through the inductor. And as you can see, at time 0, there is no current through the inductor, because that's the rule for inductors. Just like the rule for capacitors was that assume at time 0, when you apply your voltage, the capacitor is a short circuit. Inductors are the complete opposite. Assume that they're an open circuit. This inductor, at time 0, when you flick this switch like this, and there's no magnetic field in the inductor, as soon as you flick that switch, no current flows through there at all, due to the inductance, the magnetic properties of the inductor. It resists the flow of current until that magnetic field builds up. So it starts out at 0. So the current starts out at 0, and it has an exponential rise like that. It's the same 63.2% for the one time constant. Once you get to 5 time constants, good enough for Australia. It's within 1% or less. And because the inductor is effectively an open circuit, no current flows, then the voltage across the inductor is going to equal V, because there's no current through the resistor R, Ohm's law. There's no voltage drop, so it must start out at, I didn't put the maximum in there, but it's V max, it should be V. And it starts out there, and it decays like that to 0. Once that inductor is what's called saturated, magnetic field is saturated, and it can't hold any more magnetic field in it, then you're going to be at the point over here where it's basically a short circuit, because an ideal inductor, remember, it's just an inductor. It has 0 resistance in the coil, but of course all practical inductors have a series DC resistance, so it's not going to be precisely 0 like this. You'll have to use your voltage divider, which we've looked at in previous videos, and then you'll have R with the in series with the DC resistance of the coil, and that's what you're left with. If you leave that switch on long enough, it'll eventually decay down to whatever the DC resistance of that coil is. But in theory, 0. Now, when we discharge the inductor, a really interesting thing happens compared to a capacitor. You remember when we had the capacitor there, it had the charge build up on the capacitor, and when we moved the switch over and discharged it, it stayed like the same voltage, V maximum, and then it slowly decayed. The voltage slowly decayed like this. Inductors, something weird happens. You remember the negative in Faraday's thing over here, which is Lenz's law, and I won't go into details, but basically when that magnetic field starts to collapse, because when we switch this put this switch over to here like this, we've got the energy stored in the magnetic field in the inductor, and when you start discharging the inductor, the magnetic field starts to collapse, and when that happens, this negative sign comes into play. The inductor will do what it has to do to keep maintaining the current flow in this direction, and that means when we were charging up, it was positive and negative like this. But when we start to collapse that magnetic field and discharge this inductor, I can't get rid of that, damn it. This changes voltage like this. Aha! And this is a big trap for young players, and but we can actually use this also to our advantage. But if you actually don't discharge it through a resistor like this, if you just put the switch in the middle, just open it so there's no current flow, the magnetic field still starts to collapse. And when it does that, in theory, because there's no current flow, it generates, and in theory, generates an infinite negative voltage across that inductor. In practice, it's never infinite, but it's very high. And this is why you can get large voltage inductive kickbacks, and these are very useful in some circuits like your ignition coil in your car. And that's how you can generate like large spikes and things like that to actually, the magnetic fluoro ballasts in the old fluorescent lights, for example, the collapsing magnetic field generates a large voltage which then creates the arc and starts up the lamp. That's how the starters work in the magnetic fluoro ballast. You can actually generate large voltages by collapsing a magnetic field. And this is why inductors have some uses that capacitors don't. But because of that, inductors, what are they used in? Relay coils, of course. So if your chip is driving a relay coil like this, and then once you actually remove the current from the relay, then the magnetic field of the relay is going to collapse. It'll generate a large negative voltage on the inductor, and well, that could blow your circuit up. So you've got to have reverse diode protection on your coil like this. So you'll put a reverse bias diode on there so that when this collapses, this is positive, this is negative, your diode will conduct and it will clamp the voltage across the inductor to negative, well, 0.6 volts or negative 0.6 volts. So that's why you can protect your circuit. And that's pretty darn essential when you're driving relays or any other inductive loads. And you can see how I said before that when the magnetic field collapses, it wants to keep the current going in the same direction. Well, you can see why, because if let's say we flick this switch to open and there's no load whatsoever, then the voltage reverses like this and it wants to flow through the diode like that, because that's your anode, that's your cathode, and the current is still going in the same direction. And to do that, it's got to flip the voltage. That's just what happens. Can I beat the laws of physics, Captain? So what actually happens, we go back to our characteristic graphs like this, we have to actually flip these over. Well, this actually becomes V like this, okay, but it actually becomes negative V. So this will be minus V down here. So when it flips like this, it'll start out with that negative voltage, as I said, and it'll be the maximum, which is equal to V, what it actually was, the source actually charged up to. And the current will actually start up here. So this will become now this will become our current, and it'll start at a maximum if the current is still positive, because as I said, it still flows in the same direction like that, which is different, opposite to what the capacitor did. When we're discharging the capacitor, when we're charging the capacitor, current flows in this way, but when we're discharging the capacitor, it flows back out this way like this, because the voltage is still like this. Inductors operate opposite. They flip the voltage like this and current still keeps going in the same direction. Not really intuitive, but that's how the physics of collapsing magnetic fields actually works. So yeah, it still starts out, if this is like, if we charged it up at like an initial 100 milliamps, or if it was 100 milliamps up here, it'd start out with 100, if we discharged it through the resistor, it'd start out with 100 milliamps here, and then it would slowly discharge to zero as the voltage on the coil just dropped away to zero. Ohm's law. But then, like I said, if you leave that switch open, if you've got that magnetic field and all that energy stored in there, and you open it up, there's no, what does it do? This voltage doesn't go to minus V like this. It goes to as far as it can go, given the physical limits of the actual inductor itself. So you can get like hundreds of volts, thousands of volts when you only charged the thing up. When your source is only like a couple of volts or 10 volts or something like that, you could get hundreds or even thousands of volts. It depends on the magnetic properties of the inductor and the amount of inductance you've got. So, scary stuff. And there's more physics to inductors as well, but I won't go into this. Video has been more than long enough. Geez. RC and LC time constants, we covered a lot of stuff. We've been at this for like half an hour or something. So yeah, but it's interesting stuff. Inductors, it can not only have traps for young players, but it can also be very useful for generating large inductive voltages, which you can actually take advantage of. It depends what you're trying to do. But yeah, capacitors have energy stored in the dielectric, in an electric field, and inductors have their energy stored in a magnetic field within the coil itself and within the ferrite or whatever material is used for the inductors. And maybe we could go further, well, probably you have to go further into this if you start going into transformer theory and stuff like that, which is a video down the track. So the next thing that follows on from this video logically is energy stored in capacitors and inductors. And I've actually done a brief video on this on my second channel. The energy equals half CV squared like this. And that half's a little nasty thing when you start talking about charging and discharging capacitors. It's a real sneaky math problem, that one. Anyway, I'll link that in down below and probably at the end somewhere if you haven't seen that. It was just a test video, but I decided to talk about this. I'll leave it out of this video. So the rise and decay of voltages and currents in capacitors and inductors. Real interesting stuff. So you'll be using your confuser a lot for doing these sorts of stuff. And we've only talked about the case where it goes to 100%. If you've got a case where it like only goes up to like here and then starts to discharge again, then, well, you've got to substitute your maximum value for, you know, like it's still 63.2 here, so the time constant thing will still happen like that. It just like starts and ends at a different value. It sort of like never gets to there. And you'll get this in like your 555 timers and your other RC time constant circuits and things like that. And RC time constants used pretty much everywhere in electronics, whether it's in you know, your microcontroller, for example. You might think, well, where am I going to use an RC time constant in a microcontroller? Well, for the reset pin. I've drawn it here. If you've got the reset pin of your microcontroller, you want when you power up your circuit, you want your microcontroller to have a nice clean reset. You don't want to do you know, weird stuff while the voltage on your power supply is rising up. No, you want to keep your microcontroller in reset, and you can do that. Let's say it's not reset like this. So if the pin is 0, then it's reset. Well, that's what you have a capacitor and a resistor for like this. The capacitor will keep your reset pin low for the time constant using the formulas that we've looked at until the voltage on this pin reaches, this will be a Schmidt trigger, by the way, and I've done a video on Schmidt triggers because, well, you don't want to use your regular gate in there. Anyway, linked in Schmidt trigger video if I remember it, and then it'll hold the processor in reset for, you know, X milliseconds while the power supply rises up, and your processor's not going to do funny business. It's going to have a nice, clean start. So, you know, using RC time constants for your digital stuff, used all the time. So this basically ends our DC fundamentals series that we've been doing. How many? 5 or 6 videos or something like that. Pretty much after this, and energy stored in a capacitor and inductor and stuff, after that, you pretty much have to move on to AC. DC, done and dusted. Beauty. So anyway, I hope you liked that video and found it useful. If you did, please give it a big thumbs up. As always, discuss down below. Catch you next time.